Hello, everyone. How are you? Good. So, welcome to networking class. Today we're gonna start with the second to last week about like programming and electronics stuff. That is gonna be starting to make things communicate with one another. So the idea is that we're gonna do today and tomorrow we're gonna do, well, actually this week we're gonna have 3 classes. The first one today is gonna be an introduction for networking and communication. And we're gonna talk about 2 types of communication. The first one is wired communication. So what happens when we have short distance or reasonably short distance and we can talk using wires. And the second part is going to be the over-the-air communication. Yeah, I mean, I thought they were on. They're on? Maybe they need a little bit more volume or?
No, hay que hablar más cerca.
Yes, it's about to talk closer.
Okay. Okay, so the idea is wired communication and over-the-air communication. Today we're going to do 2 types or one example of each. And tomorrow we're going to go deeper into each style. And on Friday, we're going to go on the internet. And we're going to have a class by Guillem about what is called the OSI model. That is basically the model that follows internet communications and networking in like modern communications technologies over the internet. That is going to be a reasonably advanced class. That is going to happen, well, tomorrows and Fridays will happen in the academy. And we will try to make them at least today and Friday as hands-on as possible. And tomorrow will be a little bit more of theory and reviewing some. Tomorrow you will see that there's a lot of information because there's a lot of protocols and a lot of possibilities. Okay, so for today, what we're going to do is we're going to start with wired communication, and then we're going to talk about over-the-air communication. For wired, we're going to talk about the famous I2C protocol. And for Wi-Fi, so for over-the-air, we're going to talk about Wi-Fi, and in particular Mqtt, which both of them represent 90% of the cases in communication of the projects that you will do. So a lot of you will do either something that is related to I2C because you have digital sensors or things like that, and you will pass data using Mqtt protocol over the air to, I don't know, a broker that then ingests and plots some stuff. So we'll do one example of each, and we'll talk about it. Tomorrow, I'm sorry, but it's going to be a lot of information, but it's the way it is because there's a lot of protocols. And well, sometimes you have to just do it so that you have all the possibilities. And that's that. And then Friday, we will enjoy a little bit more with some hacks and stuff from the internet with Guillem. Okay? So let's start. I guess that the class is already there. Yeah. So if you go to week 14, networking and communication class, I'm going to start with wired communication. Then we will take a little break. We will talk about Mqtt. And in both cases, I would like you to have ESP32s at hand. If you don't have any, there are some around here, and some breadboards and wires and jumper cables. And if you can organize in pairs or in groups of maximum 3, so that you can, the whole class is going to be about trying to make these 2 protocols work. So The idea is that you have at least one ESP32, some wires, some per cables, and a breadboard, and a partner. If you want to do it alone, it's fine, but it's funnier to communicate with others. So, talking about wired communication, the idea is that we have physically our microcontrollers are near to one another or are in close proximity somehow. This is not necessarily true. Like wired communication also works with very long cables, but you have to take into account that generally there's signal attenuation over the cable, and that means that generally you don't have very long distances. For the microcontrollers that we're going to use, and especially for I2C, the maximum distances are around 10, 15, 20 centimeters. You can go a little bit further than that, but then you run into certain instabilities in general, okay? For wired communication, we will see that the possibilities are almost endless. Of course, nothing comes for free. So long distance also reduces bandwidth, and that means that you cannot have as much data, but still it allows you to communicate things that are very, very far away, kilometers apart or even more. Okay, so let's start with wired. The idea is that we want to make two microcontrollers talk to one another. And there are several ways to do it. And I'm going to introduce you to different categories first, and then we will try to put I2C in one of those categories. The first one is that imagine that we have a lot of pins between both microcontrollers, and we can send the information, let's say, with a lot of pins at the same time. Yeah, like in this image in here, imagine that you have to transmit 1 byte, and you have 8 pins. So each pin could transmit a bit, right? That means that you need 8 pins available, and that you're going to send the information in what we call parallel communication. Meaning that, and probably you have seen this type of connectors in the past. A lot of machines have them, and some old computers, machines, other TVs, etc., that have a lot of pins. That's because they transmit the information in a parallel sense. So all the information is going like in waves in all of the pins at the same time. There's also a clock. Normally you'll see this type of another pin, an extra pin that needs to, let's say, mark the pace on the rhythm of the orchestra. It's like the orchestra director that is like marking to each of the players how to play, let's say. So this clock is the same, which basically says whenever there's 1 in this clock, expect information. Otherwise, don't expect anything, right? And that can happen very fast. As you can imagine, sending information in parallel is very, very fast because you have waves of information coming, let's say, all at the same time. However, this is very uncomfortable because you have a lot of pins. And that's not normally the case, especially for a lot of microcontrollers. You don't even have 8 pins that you can use for digital communication. 80 tiny, 44, 6 pins, 45. All these ones have less than 8. So you couldn't even transmit a byte. You have to make magic things, and that's why serial interfaces come into play. In serial interfaces, you would do the opposite. You only have 1 pin that sends the data, and the other one that marks the pace. And basically, all the information comes in series because it goes only in 1 pin and comes one after the other. The clock pin is basically the same, marking the let's say the pace for the communication. And as you can see, anytime that we have a 1 in the clock signal, there's a bit that is being transmitted. In the same way, well, advantages for this is that we have only 1 pin, and that in principle it should be slower, but nowadays the clock speed of the microcontrollers have made this possible to be very fast. Okay. Another type, what could we do? We could send information in a synchronous or an asynchronous way. What does that mean? Asynchronous way, it means that both ends don't have this clock signal that we had in here. Basically, both of them agree on a communication speed beforehand. And that's the case of serial communication that you use, sorry, the USB communication that you use when you connect with your Arduino, that you have to select and declare the 9,600 volts or the 115,000, etc. You set that in the Arduino and you set that in your computer on the serial monitor, and then they both talk at that speed. But there's no clock signal in there. There's only actually in the USB, well, serial communication, there's only two cables. One is transmitting, so TX, and the other one is receiving, so RX. But in this case, there's no way for them to synchronize. Let's say they have to know beforehand. The other case is the synchronous one, which is the case that we already saw, which is having a clock and data going in separate lines. And they just agree on it based on the clock signal. Which one do you think is more stable or faster? Synchronous or asynchronous? Or advantages or disadvantages in general?
Not everybody at once.
Less wires for asynchronous, I mean. Asynchronous, sorry?
Asynchronous might be faster.
Theoretically, it could. But what do you think happens at high speeds if you don't have a clock? What, elaborate on regulation? Let's frame it this way. What happens if there's an error? There's no way for you to know that there was an error on asynchronous communication. You just receive things and that's it. So it means that you cannot risk going very fast. You have to know that, you have to think that there's always going to be an error, always. At least one packet, something is going to be lost in no matter what type of communication, and you have to check for that. We'll see tomorrow actually how to check for these things. You can make something called is CRC that basically checks that the communication arrived correctly. But in this idea is that ideally you would like to go as fast as possible. And with asynchronous communication, there's no way for you to know that there has been a packet lost because there's no clock for you to see. And you cannot come back or ask again, or at least in this one, you know when there's a packet coming. And if there's not a packet coming, then you know that something happened. That's, I didn't get it, sir.
You have more wires in the circuit. You have the electricity going to the current wires. If you have more pins, which perhaps like those and off or something, wires.
Yeah, in this case, still if the communication is in one direction, it's only one wire, which is good. And yes, there's less possibility of having interference in one wire than in two. But if you want communication in both ends, you still have to. Nevertheless, interference is going to happen if it's going to happen. And in these two, between them, there's no interference. All the time, as long as you put the connection, it's running. Well, things are not as simple as this, but when you're going to send a package, you have to do a certain code and we'll see this tomorrow, okay? But you have to do a certain, let's say, rise and fall procedure, and that marks the beginning of a package. that is a standard for, and that you cannot do it in here because it goes in synchronization with the clock. So the clock is something that like says like that, and then you are talking up, and whenever you do this gesture, if you not say a specific word, then it means that there's an error. Yeah. So clocks are like checking points. Clocks are more like the, as I said, like the director of the orchestra. That is basically telling, let's say, the pace at which you have to run or play.
It's like a metronome, you know, the tick, tick for playing music. So you actually follow the compass. Will be kind of.
Basically keeps you in place with the pace. Okay. So some examples of all this. Asynchronous communication, you know very well this one. You have used it already in Arduino. It's the most common one. We call it serial communication, also RxTX, and now that you are experts in this, you all know that Rx has to be connected to TX because the receiving end of one is the transmitting end of the other, and then the opposite. In general, all circuits and all microcontrollers that have to communicate with one another have to serve the ground. And I always like to say that it's impossible for you to know if I stand up in here, in this platform, if I am taller than Paco, if he stands down there, because we don't have the same reference. We have to be on the same plate or in the same surface so that we are able to measure our height. So with voltage happens the same. Ground is called ground because it's the reference for both of us to measure voltage, the same as height. So always, even if there's just two cables in serial communication, you always have to serve ground because what is 5 volts on one side, it would be 12 on the other, and that doesn't mean anything. Okay. Advanced stuff, we're gonna just skip it. Something quite common in microcontrollers is Uart, which is an universal asynchronous, well, it's basically the serial protocol for microcontrollers to talk with one another. Normally, they're implemented in hardware, but if there's no hardware, you can use one library called software serial that basically implements that or serial communication by software. So if you have digital pins that can go at a certain speed, they will implement what is called bit banking, which is just sending bits very fast and resembling serial but made by software in a script that runs this communication in a quick fashion, let's say, without having dedicated ports for Uart. In here, let's see where they are. For drivers.
With microcontrollers that don't have like hardware serial embedded on the pins and you are using software serial, you have a constraint of the maximum speed that you can use on the communication. That means you cannot use like the fastest speed of communication because the pins, they don't allow it. They are not designed to work that fast. So usually when you are using software serial, you are constrained to slow speeds that are even so like quite fast. But
okay, so that brings us to the most common serial communication ever that happened to be, well, if you have picked at the beginning of the class and I would have said, well, parallel communication or serial communication, which one do you think is going to be the most implemented nowadays? Knowing that parallel communication means faster and that connectors can be very small and that you can put a lot of pins in the same connector like USB-C. What would you say that is the most implemented? Parallel, just knowing that. Would you say parallel or serial? So finally, because of markets and things like that, is serial communication. And there's a consortium called the USB consortium that pushed basically standards for USB connectivity. And you would have heard USB 1.0, 2.0, 3.0, etc. That are different protocols in serial communication in a universal way so that all devices talk the same way. And you see, and you know already how they look. They normally have 4 pins. 2 of them are for voltage and ground. So basically voltage reference. And then the other 2 are data that are not the same as transmitting and receiving pins, but are sending data in what is called a differential pair, which basically the data is sent by the difference of the 2 lines and not by just 1 line. So normally you would say the data is sent from as the difference between data and ground, but in this case it's not. It's sent as the difference between data plus and data minus. That's why you have 2 data lines. They are quite standard, and you can use, and you have used very likely already these things on your boards when you solder a micro USB or mini USB. They are all the same. The only thing that changes is the format, and in different versions, the amount of the speed, of course, and how much current they can send. I think USB 3 is 2 amps.
Maximum depends, like up to 3 amps. Actually, USB 1.0 is like 200 milliamps. USB 2.0 is half amp. USB 3.0 is 1 amp, and USB-C I think is 3 amps of maximum output. But that depends. As the USB-C right now, there is a problem because there are standard, but not a standard in the maximum power transmission. There are different standard protocols for USB-C right now.
Okay. So that's more or less for USB. USB, I just have to say that it's not easy to implement. From experience, if you don't have a microcontroller that supports USB, it's not easy to use it. And if you want to put USB on your board, make sure that the microcontroller that you're going to use has already implemented libraries for USB, because otherwise it's not an easy thing to implement. And I say this from experience, not just making it up. What you would do normally is what is called TTL, or a serial to a serial bridge, or how is it called? My head is gone. Un chip ATTD, un serial to TTL.
Sí.
Pues
ahora mismo no me lo sale el nombre.
Exactly.
Sí,
yeah. So basically, if you don't have a microcontroller that is able to talk USB, normally what you do is what you have done already from the beginning of the Fab Academy, which is use one of these things, USB to TTL, either on a cable or on a chip. And you have done this already because you either come with USB onto your board, and then you have an FTDI chip that is a complicated thing to solder, to say nice words, or you have an FTDI cable that already talks serial communication. But don't confuse USB and Uart. And to explain that better, let me just, because I see some confused face, so I'm going to draw a little thing. And let's just make sure that you all understand this. So what you have been doing so far is that you have your microcontroller that doesn't talk USB, right? But it talks what we call Uart, which is the universal RX-TX, right? So imagine this is RX and this is TX, right? What you have done in 2 options is option 1 is to have the cable, the famous FTDI cable that basically has USB on one side and the 4 well, actually 6 pins. That is Uart or TTL. TTL is transistor logic, right? No, I don't remember. And USB on the other side. And there's a small chip in the middle. That is what we call the FTDI chip, okay? And this is all in a cable.
Time to life.
Time to life. Okay, so this is all in the USB, and then you have the cable, and it goes right there. Yeah? You are clear with this, right? You have used it many times. The second option is, since you want to talk USB because you have a laptop in here, is that you have in the board, imagine that this is the board with your microcontroller. You have this same chip, the FTDI chip, that talks RxTX. And then on the other end, you receive USB. And this chip in here is the same. The FT230XS that you already have suffered soldering if you have ever soldered up Arduino, and a micro USB. Yeah. And then, of course, on this side, you could put whatever connector you want. It could be a header connector that sends the same lines, or you could put a micro USB, mini USB, whatever you like. But at the end, you have to convert from USB on this part. You have to convert from USB here or here to TTL, so that you are able to, or Uart, to go to your microcontroller. Some microcontrollers will have already USB implemented, and it will be easy if they have it. Normally, they are like, I think at Mega 328, I think it was somehow easy. Some at Megas, the 16 and 32, they are not easy to implement, if I remember well, because normally USB cores and things like that are, let's say, less open source in general. So it's not as easy. And as you see, these chips in here are very commercial black boxes that there's not much to modify in them. They just make the conversion, but there's no, Adrian was asking if we could modify the firmware inside. I've never done it. I don't know if you succeeded, but basically what is inside for us is a black box. And that same thing more or less happens in the cores that talk USB in the microcontrollers. So it's not an easy thing.
El 32 U14, U4.
El U4, sí.
U4, sí, los que terminan en U, U2 y U4 son porque tienen posibilidad.
Pero el U2 yo sufrí muchísimo para hacerlo con Antonio.
Aunque sea el U4 y el U2, todos son manitos. Son bastante poco
abiertos.
No, y consistentes. Por eso el nardo de problemas.
Okay, so what you will see normally in an Arduino or in any microcontroller or any board that has a USB connection is that you will have your main controller. You have your main controller, and then here you have a bridge. We call it a bridge, basically converts USB, and that is yet another chip that sometimes is even more powerful or the same as the main one, and that basically does the conversion between USB and TXRX. And here you see the two LEDs that basically mark the communication and that blink when you are flashing your device. Yeah. Other interfaces in here, just for you to see, this other connector in here is the JTAG connector that basically has direct access to the microcontroller. That happens when you break or you make a mistake and you brick this microcontroller. You have direct access to it to flash firmware, but it doesn't go through USB or anything. It's a total different protocol. Okay. So going back to the purpose of today is time to talk about synchronous communication. The idea of synchronous, there are two main protocols in there. The first one is I2C and the second one is SPI. I'm going to go briefly into both and then we do the example of I2C. So I2C is basically a protocol that has a format like this, in which you have one microcontroller, well, a bunch of microcontrollers in what we call a bus that is just comprised of two lines. One line that is SDA and the other one is SCA. It's very simple. CL stands for the clock line, DA stands for the data line. And it's a very simple synchronous communication protocol that can have multiple things connected on the bus, but that one of the let's all look at Tarek. That basically, even if all of them are connected on the same bus, there's one that we call the master, and the other one are called slaves. You could call it different ways. Maybe master slave is not the best way to call them, but basically you have one main microcontroller that is, let's say, the one that is able to ask for things, and then the other ones are just, let's say, reading or acting. This could be sensors, this could be LCDs, or this could be whatever other thing like actuators and many or anything in general that has basically implemented an I2C communication. The communication is quite simple. We'll see how it works, but it only requires two wires and of course voltage and ground. Each of these devices in the bus has what we call an address, which is an X identifier. No, it's not X. It's, yes, it is X. That basically refers to, like, is the way for each of them to know who is in the bus. And it's something like 41, 44, 86, whatever. They cannot, and there cannot be devices with the same address on the same bus, because otherwise they collapse and they don't know. Slaves, they cannot talk to one another. Master can talk to slaves and request things. Slaves can send things back to the master or act on whatever request that the master does, but the slaves are basically passive and they only act when the master asks. So the slaves don't have autonomy or possibility to talk with one another. Mm-hmm. Sorry? No. No. Normally they are defined by by hardware. So the chip itself has its own address implement. Well, no, sorry. I said that wrong. Depends. Addresses are defined by software, and it depends if you have access to that code or not. If you have access to the code, you can for sure modify the address. If you are writing communication, and we will do that in a second, between two microcontrollers in which you write the firmware for. If you don't have access to the chip itself, for instance, you have a commercial sensor, they normally give you two possibilities, sometimes even more, with jumpers, so that you just solder a jumper and then it changes the address. Normally, that only happens for things that are meant to, let's say, be on the bus and that can be replicated. For instance, some type of sensors or some ADCs, etc. But normally, you cannot change the address from the master side to a device that has already an address set by itself. It's the same way I cannot change your name because you will always be Tarek. I will never, if I was the master in the I2C bus, I couldn't change the address of other devices. Yeah. There are ways to bypass that, but that is a little bit more advanced. Normally you can't. And the idea is that you do it by hardware, so that we might modifying a solder or solder jumper or something like that. Okay. So if you want to know about I2C, this application note is quite interesting. It's a little bit advanced. And this is more or less what we were talking about earlier. How do we know that there's communication happening, and why is the clock signal the way it is? Well, it actually is not always the same. It's not always running up and down, but there are some transitions that then mark the initial communication, like the beginning of the communication and the end of the communication. And they even perform something called acknowledge, which is basically an event in the data line that basically says, okay, I received the data that you sent me. And that is something that is interesting that you implement, either using I2C or any other protocol that basically says, okay, I tell Adrian, please, Adrian, hello. He acknowledged that by saying that, okay? And I know already, so we have to implement it somehow. And if I give you another order, for instance, please do something in 5 minutes. I'm not gonna be waiting 5 minutes for you to tell me, okay, I did it. No, I want you to tell me, okay, acknowledge, I will do it. So that this type of things is always interesting to make these connections or these protocols. And for instance, Josep made a very good example on his final project on the ukulele. Maybe you could show it later. That implemented communication between the different, like all the buttons that had in the, how do you call that, the mast on the ukulele. And there was like a protocol that he defined, even if it was using I2C, but the procedure in which they talk to one another, it was defined in a safe way so that it actually worked. Because if you just trust that the communication is going to be sent and you don't receive any acknowledge, or you don't check that it's actually received or anything, then at some point there's going to be an instability and you lose something and it's gone. Okay. Also, the thing here is that we're talking about normally I2C sends packets of bytes, of 1 byte. So you have to think about compressing information. You normally don't send a string. You codify something, and if you want to say hello, you send 1 or a 2. If you want to say goodbye, you send a 4. But you don't send the whole string in Unicode that takes 256 bits. You send something very small, and then both ends say, okay, this means something, this means something. I establish a communication that is very light, okay? Super quickly, before jumping into example, is the other very common asynchronous communication that is called SPI. The ones that have done a FAB ISP have already used this. It's normally the 6-pin connector SMD that has, let me just show you. This connector in here, that is SPI and has 6 pins. What are those 6 pins? Are voltage and ground, the clock, SCK, the same as I2C, and then MISO, like the soup, and MOSI. MISO is master in slave out, and MOSI is master out slave in. Okay, this works more or less like this. So the idea is that you have the clock that is being defined by the master, and then MOSI is like having I2C, but in 2, instead of 1 data line, you have 2. And the communication from the master to the slave goes from MOSI to MOSI, and from slave to master goes from MISO to MISO, okay? Then communications happens more or less like send a clock, send a message, wait for response, then the master receives something that the slave is sending, and the message is happening in that manner, more or less, Okay, this is a little bit more advanced, let's say, and it's quite common. A lot of sensors use it as well, but it's far way less common than I2C. So that's why we're going to see I2C today. But SPI, again, if you find something, don't be afraid. A lot of library. Well, there's SPI library in Arduino and a lot of examples. Don't worry, it's not that complicated. It's just a little bit less common.
What are the benefits
compared
to I2C?
Yeah. Let me reread. I don't remember, honestly. Speed benefit, I think, to respect to I2C is the speed of communication. And that's why normally SPI is used for flashing microcontrollers, because it's very, very reliable, and that means that you can go very, very fast. But honestly, for low level or for low-fi applications like sensors and things like this, I2C is more common. You don't need as much as reliability, but if you want to go fast, SPI is the way. Okay. One thing about library is that I2C uses one library called Wire, Arduino library. SPI uses SPI library. Also for I2C, you will see that there are some other wire libraries. For instance, for ATtiny, there's a library called TinyWire that is a little bit smaller and implemented for ATtinys. That is even split into two: TinyWire slave and TinyWire master. So TinyWire S and TinyWire M. The reset one, I'm not fully sure, but normally microcontrollers, when you want to flash them, they need to be reset at some point. And before the bootloader section, so when the bootloader loads and before going into the flash section, you have to reset so that you're able to unlock the flash and send data into the flash and write the flash memory to flash your firmware. So that pin is used to pull down normally and reset the microcontroller and then be able to write the flash. Yep. I don't know if it has any other purpose other than that. Okay, and here this is what you've been doing already. Just an example of you with your, well, actually not with your computer, but something very similar. Seriously? So this is your computer in here, so that you see the whole, when you flash a microcontroller, you have USB in here, then USB to USB TTL converter to TXRX, then the ISP or the bridge on the board, and then the MISO, the SPI protocol. So when you flash using the FAB ISP, you are actually using 1, 2, 3 protocols at the same time with 2 different bridges to establish the communication. Okay, and that all happens, let's say, out of the box. So that's it for wired. Now let's talk about I2C, and let's start doing some examples. So for this, there are some examples on the networking examples part. And here, if you go to I2C, please load your ESP32s and find a partner, some jumper cables and breadboards. One of you is going to be the sender. So it's going to be sending information and it's going to act as master, and the other one is going to act as a slave. You have the examples here, and we'll go through each of the tables to help you so that you are actually put on the spot a little bit with pressure. But basically, it's just replicating this in here, okay? Remember, ESP32, you have to find a pinout that has and that details where the I2C pins are, that are, look, where are they? Okay, so here you see pin 11, in this case, is the SDA in here. And SCL is pin 14. So find a pinout for your board. If you are using the feather, just use the feather. If you're using one of the ones here, find the pinout. Find voltage, ground, SDA, and SCL. Be careful with voltage. ESP32 works at 3.3 volts. So voltage that you share has to be at 3.3. And try to run in this, sorry, where is this? Here. Try to run these examples in which basically we begin wired communication and we send a hello, and the other one just reads it. So you can include serial communication to your computer and print the messages. And if you go a little further even, you could send messages between computer and computer using the boards as a protocol for communication, okay? Yeah? Do you all know more or less where this is and what you have to do or no? First thing, find a friend. Second thing, have your boards. Third thing, find cables and breadboard, computer, stuff like that, and then open the documentation, find examples, and run it.
Do you all have ESPs?
Who doesn't have ESPs?
Who doesn't have a ESP?
Me too.
Estos, ¿no? Dos. Your Arduinos are ESPs also. You can use them. Voy a poner.
Ya de la caja amarilla.
Ah, female está bien. The female no. Hey guys, in terms name, number, female, or table six, I recommend. Down. Here, people at home. So if you have two microcontrollers, doesn't matter what type, it's great. Otherwise, let me think. But do you guys have two microcontrollers or not? At home, at least two Arduinos or something.
I have one. I have one.
Okay. Come over. Sorry. Okay. Here. So Kurt, Ivan, the rest, do you have two microcontrollers?
I have one.
You have one.
I have to.
Okay.
I
So,
can't really exercise.
and do you have any digital sensor or similar?
I think I have. I need to check it.
I can hear you.
Can you hear me?
Hear you.
Can you hear me? I think I have. I will check it.
Maybe you could write it on chat. Maybe you have one. Carla has two. I have 8020, 1614, and ESP32. Okay, so one by one. Diego and Neil, yes, you can use Arduino, our 80Tiny, and ESP32. Kurt, you're okay. Carla, you're okay. And Ivan, if you have, okay, the code is in here. And then Ivan, if you have a digital sensor, find it and let's see which sensor it is. And then we can try to, like, let's find a library or something like that to talk to it.
Do you have another ESP that I can use?
Yeah, use that one, please. Hola, hola, hola. Sí.
Hola, hola. Hello, hello, hello. Hello, hello.
Microphone.
Hello.
Okay, now you can talk, Ivan. Sorry, it was a misconfiguration of the speakers here.
Okay, can you hear me now?
Yeah.
Yeah, I have one microcontroller and I will try to find some digital sensor. So
What microcontroller do you have?
I have is Nano, Arduino Nano, that the one
Okay.
that has no.
The SAMD.
Yeah.
Okay. So, well, for SAMD21, there's
no,
a.
no,
Yeah.
not like that. I will show you. Just a sec. I have like this. Is this a nano or micro?
Okay. Okay. So that is 328.
Yeah, 328. Yeah, 328 mega 328p.
Okay. So that one has I2C, if I remember well. Mega 328. Yeah. See? And then we have to find the P. If you find a digital sensor, then we can use that one.
Okay, I will try to find some.
Yep, perfect.
Okay, thank you.
No problem.
I2C es el pin 1 y 2, ¿no?
Es el, bueno, 2728. No sé si son de Arduino, los de Arduino son los mismos. Ponemos límite como a las 12. Sí, para hacer un break, ¿no? Sí. Just one thing. We want to do this before noon. That's right. 4 y 5. Aunque tengo un nano. Hello. Hello. One thing is we want to do this before noon so that we can do also the Wi-Fi part. Okay.
Son los mismos. Suelen, los pinout del Arduino son lo mismo de igual.
El P3 no tiene los pull-outs.
Okay, please one moment for attention, please. In I2C protocol, let's have two microcontrollers. 1 second, please. You have voltage, and then you have ground, and you have both lines, SDA and SCL. Between two I2C devices, as you already know, there are these 4 lines, and very important is that SDA and SCL, they need to have pull-up resistors, normally of 10K. Okay. ESP32 on none of your boards apparently has inside those pull-up resistors. So you need to put pull-up resistors on both lines, on SDA and SCK. I just leave this in here. These pull-up resistors, don't take them for granted. They are normally 10K, and you will almost all the time they will be 10K, and you would be restricted to 10, 15 centimeters. If you want a little bit more of range, like 25, 30, etc., you can reduce those pull-up resistors. And there's some application notes on the documentation on how to calculate them. It's not an easy process, but normally 10K, and if you want a little bit more distance and there's problems in the communication, reduce them and try with 5K, 3K, 2K, etc. Okay? But basically, right now, we need 10K resistors and breadboards. And it only needs to be 2 resistors per group.
Everyone else has the... filters.
Those are female.
Con los pequeños talentos. Like what do you use a meeting sensor or whatever?
No, that just started with exercise.
No puedes soportar IPC Slave.
Lo acabo de ver.
Ah, va, eso.
Sí. Pues usar de momento solo comunicación de que él te mande algo a ti, pero sin un request.
No pueden ser dos máster.
No. I need dos solo para ver un master.
Vale. Y entonces, pero para que él me mande algo, yo tengo que ser slave de una manera, ¿no?
Tú puedes ser slave.
Because el wire, no he mirado bien el código. El wire request from, ¿qué hace?
Lo que haces es, yo te pido a ti algo y me lo retornas de vuelta. O sea, yo te mando, o sea, te pido algo directamente.
Vale.
El otro ejemplo es... Sí, lo estoy viendo, ¿eh? Ya. Lo acabo de ver.
Sacamos arduinos, ¿no? De la media.
Sí, hay que hacer...
Ah, con Arduino. Vale. Voy a...
Okay, one thing. Hello. So, please, there is one thing that we just realized. That is one of the examples, specifically the example in which, so if you're using the example number 1, in which you request information, this example works and compiles in an ESP32, but this one doesn't, because it's not implemented in the ESP32 to work as a slave. So you have to use an Arduino. So we're bringing Arduinos to get that running. Probably, I don't know if it works on the ESP8266. Please give it a try. Otherwise, we just have some Arduinos in here for those that are going to implement the on request.
86 igual.
No lo sé. Yo creo que sí, pero ellos prueban.
Ellos tienen 86.
Sí.
Who wants to be a slave? Who wants to be a slave?
conectar ahí. Si se le pone
Pero y si no,
si no, pues sacamos más 866. Aquí hay otro.
dáselo a estos. Okay. One thing, hello. 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 One thing. So before we had two ESP32s, and this was not working because ESP32 cannot be a slave. If you are using a ESP32, the ESP32, and this is like a perfect example of complexities in communication, works at 3.3. And if you want to use an Uno, this works at 5 volts. So in the middle, I don't know if you remember what we used to say in the sensors class. What is this in the middle? A level shifter, exactly. So you will need a level shifter in between if you want to use the Uno and the ESP32. So options that you have is either, and I leave a table here, is ESP32 with ESP8266 or Arduino Uno with Arduino Uno, but not ESP32 with Uno. This is forbidden because they work at different voltage levels, okay?
Yeah, there, no, I think it's.
Sí, sí, da toda una sesión, 10 minutos, de explicar de que Wi-Fi no es una frecuencia, Wi-Fi es un protocolo.
Hello? Okay, I'm very sorry to do this now, but we have to keep going because otherwise we won't have time to talk about MQTT and Wi-Fi. I'm really sorry. I know that you are like trying to go for it, but we need to keep going. Otherwise we will be here till 3. That's not the point. So let's keep trying to do this. I think there has been some success over there with Arduino Uno. There's some complications over here between ESP8266 and ESP32s. What we know for now, and we believe, is that I2C in ESPs only work as masters and not as slaves. And probably that's the problem. But we'll keep working either tomorrow morning with basically you are a group of academies in here, so we'll try to fix it and get it working, okay? But trust us, this thing is not bullshit, it actually works. So Edu now is gonna talk about Wi-Fi protocol, and then we're gonna have a little bit of the same thing, but using Wi-Fi over MQTT. So MQTT over Wi-Fi, sorry.
Lo tengo perdido. Estaba corrigiendo. Tengo que dejar de esa parte. To see two messages in the chat. Voy a probarlo yo, a ver.
Estoy yo con esto. No, estoy con el chat. Tú prueba con eso si quieres.
Prueba a ver que este Arduino y este y después este.
So, guys, this is now that we have seen like types of wired connections, let's see something that you are every day using on all your life. That is Ota Communications. What Ota stands for is over. Actually, what is for? Over the air communication. Like I just have a blind. So what is over the air is actually communicating without any cables or physical connection. What is the kind of oldest over the air communication that humans we have? Like before, when you want to talk between two different mountains, either you make a column of smoke and basically you use the smoke with a blanket to actually make bubbles of smoke, or you can use light, just like lighting a big fire, a fire to actually send a super basic message to another mountain. Over the years, this evolved, especially in the Navy, and they use like flags or lights, flashlights, powerful flashlights to actually give communication. What is the biggest problem of this kind of communication? When you don't have any physical connection. That is really difficult to see if the other person has received the message, no? That is really difficult to see if the other person has received the message. Actually, this happens exactly the same with any kind of over the air, like Wi-Fi, radio, etc. So first, let's go on how we transmit nowadays, or we produce over-the-air communications. We use radio frequency to actually transmit our digital signals, or also analog signals. What, for example, radio, you know there are two types of basic radios that we listen to, no? AM and FM. You know what it stands for? Analog modulation. So actually the signal of the radio is analog, and we have FM, that is frequency modulated, that we can, it's not the same, but we can simplify as a digital one. It's not exactly digital because then we have digital radio communication, that is basically an FM is PWM. So that's one of the reasons why FM has more quality in the audio, because we are giving full blast of the signal at no matter the message. Meanwhile, in analog, we are actually need to change the intensity of the signal. That's why we have some little of background noise in AM frequencies. First, we need to understand type of frequencies. That is basically the wavelength size. So lower bandwidth or lower frequency, the wavelength is way bigger. It can become so huge that a full cycle can measure like 100 meters or 1 kilometer, For example, like space, actually we get to know in the space like NASA reads this kind of frequencies, like super big wave frequencies to actually discover planets and get the particles emission of other planets. And they do, for example, I think it's Arepo telescope, the one that always shows in the movie that is in the mountains, I think it's in Costa Rica. That is a radio telescope. What basically it measures is not with optics or with, and not with light. What it gets is just radio frequencies. And by checking the radio frequency and how the frequency is modulated, we're able to discover like other planets, other solar systems, etc. Of course, like we usually don't use these kind of frequencies because they are so huge that we cannot transmit a full message. For example, right now you are just 10 meters away from me. If the wavelength I'm generating measures 200 meters, you never will be able to get the full wavelength. So actually we use high frequency transmissions. We usually use in the range of 1 megahertz to 100 gigahertz. For example, Wi-Fi communication, what kind of frequencies it uses? Wi-Fi, frequencies we use in Wi-Fi communication. Any idea? We use gigahertz, 2.4 gigahertz, and now some Wi-Fis, they don't have only one antenna, they have 2 antennas. And they have like, usually when you go to a bar, there is like 2.4 gigahertz of the network and 5.8. That is basically the double amount of gigahertz. What goes faster usually? The 5.8. Why? If we just double the frequency, we are able to transmit double amount of data in the same space of the wavelength. It's as simple as that. What happened? These are the pros, like higher frequency, more amount of data we are able to transmit. Meanwhile, also going to higher frequencies, we have some problems. What is the biggest problems of going high frequencies? Any clue? Sorry?
That's degradation of the signal.
Exactly, degradation of the signal, or usually that's about penetration or redundancy of the signal. That is basically when you have a material, any kind of material, this is physics 101, all the materials actually stop the signal. It's like a resistor based on different things. One is amount of volume of the material, another one is density of the material, another one is like conductivity of the material. That is called, with signal, it's called penetration. How good the signal can pass through the material without losing actually the signal. For example, if you are entering in the subway, what happened? Usually you lose the network connection, no? It's really easy to lose the Wi-Fi or the 4G compared to the 3G. Why? 4G again is higher frequency than 3G, and also higher frequency than GSM, that is the basic internet connection for mobile devices. But the network, just to have phone calls, is the last thing you lose. Why? Because it uses the lowest frequency of all the phone connections. So actually, like higher the frequency, more data you are able to transmit, but you will have more problems with penetration. It's not the same having a building made out of 1 meter of walls of concrete that having made out of wood. A building out of wood, you are able to transmit without any problem most of the types of frequencies. Meanwhile, if it's made of concrete, the density and the massiveness of the concrete actually stops and jams or blocks a lot of the signals. And that is not directly related to all the signals. And if you want to simplify, and this is a huge simplification, if we have a wall that is 10 centimeters of concrete, and we took the signal X of frequency, a frequency that the middle point between the creases, that is, this is the frequency, is a space 10 centimeters, the frequency will be stopped and cannot pass to the other side. As simple as that. So more space between the frequency on the frequency spectrum allows you to pass through thicker materials. A high frequency actually bumps back. If we have a frequency, let's say, for example, a microwave, what is called microwave is super high frequency, actually. The microwave bumps back. Meanwhile, if we use, for example, AM radio uses a super big frequency, is able to pass by with a little bit of signal degradation, but is able to pass by. And when choosing frequencies, it's really important to know what kind of applications you want to choose. So for example, you want to transmit over 100 kilometers, you will need to go really low on the frequency. But the amounts of data you want to transmit are going to be also really low, or you have to send the data really slowly. For example, GPS triangulation was what the GPS does. The GPS are flying away more or less between 10 to 60 kilometers above our heads. How we are able to transmit so far? Any clue? Because GPS usually uses the range between 30 to 300 kilohertz. So actually the wavelength size is between 100 meters and 1 kilometer. So we are able to pass through what? Through all the layers of the atmosphere. That is more or less the atmosphere measured like 15 kilometers thick in the aerospatial standards. So why we don't use, why is the kind of data that the GPS gives? Any clue? Basically, it's a beep. It's super simple. The GPS triangulation is done, it just gives a beep to initiate the communication, and what is the location of the satellite. And basically, we triangulate between satellites. It's really similar to Tarek, what you want to do. So, for example, Wi-Fi is not only a type of frequency. Why? For example, Bluetooth communication also uses 2.4 gigahertz. Wi-Fi also uses 2.4 gigahertz. What Wi-Fi is a standard that uses that type of frequency. So we can have different types of communication using the same frequencies. For example, your ESPs, 32s, 8266, they have all, actually what they have is not Wi-Fi. They have a radio emitting microcontroller that emits at 2.4 gigahertz frequency. What we use is we use a layer of abstraction on top of it, so we don't control the frequency. That is the Wi-Fi standard. The Wi-Fi standard is a kind of communication protocol. Why we use that kind of communication protocol? Because if you're sending a message, you want to check that that message has been received completely. So if you want to have a simpler approach, is Jean-Luc, can you repeat exactly what I said? H, E, L, L, O. What is the message? Okay, that's the way. So actually we get package confirmations, and Wi-Fi is a really complex way and really does at really high speed with all the communication that we receive. If I just say H-E-L-L-O and I don't listen to you, I don't know if you actually have listened to me. could happen this. I say HELLO. What did you got? EO. Yeah, so you don't get the full message. Actually, Wi-Fi, what we know as Wi-Fi communication, is a kind of protocol that uses the 2.4 and 5.8 gigahertz frequencies. For example, sometimes you have been in Spain like in the last year, maybe you have to retune your TV in the last year. The TV channels didn't work anymore and you have to do the setup again. Why? Because they have changed the frequency emission of the different TV channels. Why? To put more channels. They have make the channels choice bigger. If before the channel width was between these guys, they have actually increased it a little bit, so they are able to fit more TV channels. And this is more or less in all the countries. The frequencies spectrum are controlled by the national governance that states which kind of frequencies you are allowed to use. For example, in Spain, it's forbidden to use the 900 to 950 megahertz frequency. Why? In states, it's the 433. Exactly, emergency services. It's the frequencies they use for the police, firefighters, like army communications. That means that you have a speaker that can listen to these frequencies. You are able to know what they say. No, because they use protocols, usually that they are encrypted, so you don't know what they are saying. It's not only about the radio signal and frequency that you use, but it's also about what kind of protocols you use in your signals. Say that we can actually transmit in all kind of radio signals, but everything depends on your application. Like, for example, if you just want to transmit simple packages, like I'm here, like a GPS location, you can use, or for example, what airplanes does to actually show on the map where the airplane is just super basic information. They use super low frequency radios, so they are completely sure that it reaches really long distances. But meanwhile, for example, two boats, they approach to each other, there is a moment they can actually talk with the radio. Why? Because just like the walkie-talkies, they use frequencies that are quite low, but they need to be high enough to be able to transmit audio. Audio is a heavy communication protocol if you want to heavy amount of data that you're transmitting. So actually you cannot use all of them. And this is actually something that we use right now to transmit data over the earth. Like the atmosphere also works like a wall. We use radio signals to actually bounce on the atmosphere if you use the proper frequencies. And that's how you are able to transmit data in not a straight line. You cannot transmit through the amount of dense earth that we have. What we are able to do is bounce back the signal on the atmosphere so it's able to reach the other side of the globe. And this is about choosing the proper frequency. What happened, for example, with Wi-Fi? Why the Wi-Fi doesn't reach right now to China from Spain? Because the signal gets degraded in a really small amount of space, because it has really poor penetration. Cannot even penetrate through buildings. It's not going to penetrate through a whole city. Also, we need to think that we have like the last thing is powered by distance. In doubling the amount of power of emission, we emit in watts. 1 watt, 2 watt, 3 watts, or 100 milliwatts. Depends on the frequency. Legally, we are able to transmit in some range. Why? For example, Wi-Fi, we usually in Europe is illegal to transmit or have an emission devices higher than 100 milliwatts. Why? Is for safety for humans and live beings. Is as everything absorbs radio frequencies, having too much radio dissipation on light beams might affect the cells. And actually, like what we know is like radio pollution, radio contamination. So actually, we have a maximum amount of watts that we can emit at different frequencies. That doesn't mean that if you want to hack your Wi-Fi and you double it from 100 milliwatts to 200 milliwatts, you are going to be able to reach further, double distance? No. Actually, it's an equation like this. You can double the power, but you are in general gonna get maximum 1/3 of maximum or more reach. If you are more curious about these things in networking, in the advanced Ota, we have equations to explain this. But doubling the amount of power emission doesn't give you more range. It's way more important to actually have more sensitivity on the antennas, to improve the antennas. It's more efficient. Yes. Yes. For example, ultraviolet UV, what does to your skin? Okay, actually, usually from the light spectrum and to a higher frequency, what happened is you have more frequency. That means you have more amount of energy in the same amount of space. So actually, you need to have less power to reduce the amount of irradiation that you have. That's why, for example, gamma, that if you like a little bit science, gamma is a huge problem for astronauts. Gamma, with even a small amount of power, passes through a lot of materials because the frequency is so small that passes through everything. And actually, astronauts have a time limit in the space, and we still don't know what happened to humans or light beings, and it's something that they study actively, because if we get out of the atmosphere, you are getting full of radiations of different frequencies that you don't get on Earth, and that actually kills your human cells. So, for example, microwaves are also quite bad for us. That's why the microwave is metal and is encased. If you use a microwave open, that you should never do it, basically you're gonna not only get warm, but basically what you are doing is evaporating the water inside your cells. That is basically destroying your cells. So that's why we have some standards, and usually model standards are quite similar all over the world on the maximum amount of irradiation that a human body can get per frequency of emission. For example, they say that mobile phones provoke cancer, but you get all the time the phone close to your ear. Depends. For example, have you realized that when you are in the countryside, your phone gets out of battery sooner than in the city? If you are really in an isolated place, the phone is changing the power of emission all the time, depending on how good the network is. If you're on the countryside, really far from any telephone antenna, the phone gets into maximum emission power. So it puts the phone on maximum emission power to actually try to get a little bit of signal. That what happened that does is basically sink your battery because your phone is emitting at full power. Meanwhile, in the city, as we have a lot of antennas, with just a little bit of power of emission, we are able to get network coverage. Like, for example, put your phone inside the fridge. The fridge works as an isolator, and you will see that the phone runs out of battery really, really fast, because it will put the phone in maximum amount of emission power and receiving power to actually try to get network coverage. Let's not get too crazy into that. But for example, these are standards. Wi-Fi and Bluetooth uses the same frequency, but even in the same frequency, the modulation, and a modulation is one thing is the frequency, another one is what happened inside the frequency. So inside the frequency, we have what is called modulations. So actually, Wi-Fi modulation is simpler than Bluetooth.
That's why, for example, Bluetooth gives less range. Even if Bluetooth is 2.4 gigahertz and Wi-Fi is 2.4 gigahertz, Bluetooth, you get maximum 30, 40 meters of range. Meanwhile, in Wi-Fi, you can easily get 100 if it's an open space. Because the modulation inside the signal is different. Not only on the hardware side, let's say, because radios is, we can consider hardware, but also on the protocols of communication. So actually, Bluetooth is able to transmit more information than Wi-Fi. Because the modulation at the end is a wavelength inside another wavelength. So actually, getting to know if you lose a little package here and the wavelength is simple, you can estimate it. Meanwhile, if the modulation is something like this and you lose this package, you lose the communication, but you miss the package. And what Bluetooth does is unsyncs, basically disconnects, because a protocol that what it is designed for is for stability and robustness and full data transmission. That's why, for example, we use Bluetooth for audio transmission, because audio needs to transmit a lot of data. And Bluetooth is able to transmit it in a more efficient way. Everything with the same frequency. Let's not get too crazy, but Bluetooth protocols, they work in a really similar way as I2C. We have a master and we have a slave. That's why, for example, you cannot pair like 20 Bluetooth speakers one after each other. Now you have Bluetooth 4.2 that is able to do that, but it's not that expanded. But in general, a Bluetooth communication is able to pair one-to-one device or several devices to just one master. And Bluetooth protocols, well, actually Bluetooth modules, what they do for communicating to our boards, what we use, serial communication most of the times. So actually, when you transmit in Bluetooth, you are using different types of protocols and communications. First, you are using serial communication, RX, TX. And this has a board that transforms into TTL. Actually, in some of these guys, they say TTL Bluetooth module. And that TTL is talking to another microcontroller that what it does is a radio emission module that emits at 2.4 gigahertz, but with the protocol of Bluetooth, with Bluetooth protocol, like in the coding is already embedded. How is this protocol and how it works for? This image doesn't work, I don't know why. And on the other side, we will have a symmetric system that we have a microcontroller that is receiving the information and gives packets confirmation, the same as we just did. Like, actually, it doesn't repeat the full message because there will be a loss of time and amount of data they are transmitting. They have like echoes to actually transmit the data. So for example, you will be able to see that some of them, they say packet number 1 and they say the packet, and they say packet number 2 and they say the packet. And the receiver one, they say packet 1 receive, packet 2 receive. And in case they say packet 3 receive and not 2, they repeat packet 2 to get again the data transmitted. Wi-Fi protocols, you want to go into this? I think it's better.
Sí, bueno, la verdad es que tampoco quiero entrar tan en detalle.
Oscar explains this better than me.
¿Mantienes tú tu pantalla?
Sí.
Okay, so things to take into account into Wi-Fi is that basically in the hardware implementation, the antennas are let's say they can act in many different ways. Okay, basically, the antenna doesn't need, or Wi-Fi in general doesn't need to be connected to the internet, and that's like common misconception, let's say in general, that Wi-Fi can just be a local area, a local network that just connects things, and there's not necessarily need to be connection to the outer world through a gateway, that as we have seen in the past. Okay, if you want connection to the internet, let's say normally this is called access point. Okay, which is basically a Wi-Fi antenna with an Ethernet cable that takes Wi-Fi and converts to Ethernet, and then you go into the internet. However, if you want to connect ESP32s to the internet, well, there are different ways that the antenna can work. And in the case of wanting to connect to an access point, this is called a station. You can also use your internet, your ESP as a soft access point that basically doesn't give any connection to the internet. It doesn't serve as a gateway, but just is able to create an access point to connect two stations that can be your phone or your laptop, and just serve as the, let's say, bridge between them. Also, you can do that as a mixed station and soft access point. So the antenna can work both at the same time as a client to the network and also serving as a repeater. You can imagine the soft access point in this case as being as a repeater of the Wi-Fi signal. And simply it can just be a client that, for instance, can send or like do operations based on only sending information, but not acting as an active part on the network. Nevertheless, this is all defined in the library, let's say, in the library part. And today what we're gonna do is use, on the Wi-Fi side, let's say we're gonna implement yet another communication protocol in one of the layers of communication, and we will work as clients of the network. So we're gonna have ESP32s hanging from the access point in IAC, and then we're gonna have a Raspberry Pi on the third floor in the office that is also connected to the Wi-Fi. We won't have internet. We could have internet, but we don't need it. And we're just gonna act using the access point as bridge and the Raspberry Pi on the top as a station to, or as a server, sorry, to enable communication between you guys. This is like, I think it's gonna make more complicated stuff.
So basically, what we have is like the different type of devices that connects through Wi-Fi. Actually, it's not connected to the internet. Internet, what is just multiple computers connected together, being able to send information, web pages, or music, or files. Actually, everything is a file between the different computers. So we can use your ESPs are basically microcontrollers that they have a radio emitting microcontroller embedded into them. And they emit at 2.4 gigahertz, and they have encoded like hardware Wi-Fi. So actually the radio emitting microcontroller can use the Wi-Fi protocols in a native way. Actually, for using them, you will see in the programming part that you actually need to initialize to the use of those lines of code that are embedded and pre-programmed on your ESPs. Does that mean that you can need to connect to the internet? No, you can use the same as a walkie-talkie. You can use Wi-Fi to connect to between two ESPs using Wi-Fi standards. And you can create your own, let's say, mini intranet. And what we are doing today is actually using the repeaters of IAC as an internet connection to the Pi that is upstairs. And we have if you want to have it as a box with doors, the modem and the router that we have here has a door to connect, to get out of the internet. What is that door? It's all the world internet connection. Are we using it?
we actually don't need to use it. So actually this, imagine is a flat with a lot of doors that you can just go and stay between your living room, go to your living room to your kitchen, or you can exit through your apartment. That will be the rest of the world. That will be the internet. You want to go with the example?
Yeah.
Okay, so if we go again into the example ones, let's go over classes,
Quizá hay que hablar un poco de Mqtt, ¿no?
networking, sí. ¿Dónde voy?
Vete... No, es que de Wi-Fi,
Networking examples.
¿dónde están?
Está, todo lo de Wi-Fi estaba aquí, no hay más.
Yeah.
When say you want to do communication,
Actually, the option is quite tricky. It's not simple, but as the Wi-Fi communication is simpler on the hardware side, you are able to transmit to longer distance than with Bluetooth. So first will be an option of distance transmission. Second, with Wi-Fi, for example, you get with your computer, sometimes you get a really bad connection, and your Wi-Fi actually is like connecting, disconnecting, sometimes working, sometimes not. With Bluetooth, that doesn't happen. Actually, what you have is handshakes that is either you are connected and be able to receive the full message nicely, or either you are not connected. There is no midpoints. So actually, if you have want to have a really steady connection and your data is important and you transmit, and you prefer to lose the connection over just getting half of the data, you go for Bluetooth. Meanwhile, what is important is actually to have a connection, no matter what quality the connection is, you go over Wi-Fi.
Entonces, te lo pongo en el chat.
¿Puedo compartir tú? Si quieres.
Okay.
Vale.
Bueno, lo pongo en el chat igualmente. Okay, so now what we're oh my God. So now what we're gonna do is, well, first thing I'm gonna put a link in the chat that let's see everyone. So please go to that repo. What we're gonna do now is we're gonna talk about using remote networks with MQTT. Probably already some of you are familiar with this concept, but MQTT is a standard developed for communicating devices that have to send low amounts of information, but that can send it on a periodic way. So the idea is that you have a network, or it can be wired or it can be over the air, it doesn't matter, we're gonna use it in Wi-Fi. But the idea is that you have different devices connected to what we call a broker. The broker is the one that hosts the server, and in this case is on the Raspberry Pi. And then you can have different senders that are publishers and subscribers that are people or devices listening to messages that you send. The idea for MQTT is that you send it with topics, and you can imagine topics as being in a chat room, that you can subscribe to a topic and then see everything that goes through. And you can also send things into a topic, and everyone that is subscribed to that topic will receive it, okay? Topics are separated by slashes, and normally this is very useful to identify devices, to identify channels, sensors, things like this, so that you can subscribe to only the information that you want, or all the sensors that send temperature, or all the sensors from one certain user, okay? The important thing is that there's three concepts in MQTT that you have to remember. The first one is the broker, that in this case is on a Raspberry Pi upstairs, and then the publishers and subscribers. Publishers and subscribers is a concept, but they can be on the same piece of hardware, and it doesn't need to be on separate units. They can be on the same, the same ESP32. It can be both a publisher and a subscriber. Okay. And the idea is that the publishers post and send data to the broker, and the subscribers subscribe to different topics and just receive the data on the, let's say, on a periodic way, or whenever there is data. So here, let's go through the example for 1 second, and then we'll see, I'll give you the server that you have to configure. So if you look at the example, actually, let me load it, and we will open with okay. So if we look at the example, can you see it well? Yeah. The idea is that we're going to set our Wi-Fi connection. In this case, it's just IAC Wi-Fi, enter IAC 2013, and then we're going to connect to an MQTT server. The MQTT server credentials, I will put them in here, and I will keep them on the screen. But basically, this is the IP address of the Raspberry Pi upstairs. You can use user and password, but in this case, there's no need. So it's not necessary to set them. And basically, what this example does is that connects to the Wi-Fi network, sets up the MQTT connection. MQTT, you remember we were talking about different ports the other day, port 80 for HTTP, 443 for HTTPS, 22 for SSH. So MQTT works on port 1883. Yeah. No. So a server, like a web server, web there means that you're going to share content in a text form that is used for web ideas. So basically to be visible in a browser. This, what we're going to just send is strings of just data, like just numbers and letters. Yeah, actually for MQTT is more broker than server. A broker meaning like the one that trades and is able to take information from publishers and send it to receivers. No. Okay. And basically what we're doing here is we have our loop. We check that we are connected. If we are connected, great. If not, we reconnect to the Wi-Fi, sorry, to the MQTT server. And then every second, what we're going to do is read a sensor, but you can modify it and put whatever you want in here, a number or something, and you publish it on the topic. The topic, you define it in here. Okay, the topic is like the chat room on the server. So in here, I encourage you, or what I would suggest is that you set a topic so that you subscribe on your groups, and one sends data and the other receives, and vice versa, because publishers and receivers can be, sorry, publishers and subscribers can be in the same hardware. So you can both send things and start like a conversation. Important also is to know that this concept of callback, that the idea is that the code here is somehow asynchronous, which means that whenever you receive a message, we're going to execute something. And in this case, what we're going to do is print what we receive and also blink an LED, just to highlight that we have changed that. And then the reconnect one that you don't have to touch, and the Wi-Fi either. Okay. So where is, I'm just going to say IAC Wi-Fi, enter IAC 2013, and then the Pi is in this address. And you don't need these two lines, okay? You can find, well, actually you need them, but they can be empty. Okay, if you have any sensors that I don't think so, you should put it in here, but we can delete it. And then the rest is all set. So what you have to do is modify in the middle of the loop the message that you want to send, modify the topic, find a partner, and start sending information with one another. What I'm going to do is also connect to the server. Here is the Raspberry Pi that we have upstairs. And since you come to the Code Club, you know what this is. Mqtt is a server that is a broker for Mqtt that works out of the box on a Raspberry Pi. And the broker is active, so it means it's working. And just to show how this works, I have on one side, I have the Raspberry Pi, and on the other side, I will have my laptop. And I'm gonna publish a hello on the topic hello, and I'm gonna listen on the other side, okay? So whenever I send hello on the topic hello, I receive it on the Pi. And I can subscribe to all the topics and I will see all the information passing. In the left side is the Raspberry Pi, on the right side is my laptop, and they are talking over Mqtt, okay? What you will do is the same, but with the ESP boards, okay? And for that, you need this example, yep? Is that more or less clear? You will talk peer-to-peer in this case, okay? Example, you have it in the chat, the remote class, example.ino, okay? If you want to do also with Python, if you have a Raspberry Pi, there's also an example in here for a Raspberry Pi in Python if you want, or execute it in Python on your terminal or however you want, okay? Yeah? Or no? Action, not action? Yes, no? We try? We try, no? Yeah? Do you want to try or not?
You have to do it like in 10 minutes again.
I mean, you have to do it in however much time you can, but the idea is to do it together, yeah. Okay, if you want to test that it's working, once you have the code running or in your ESP, what you can do is send hello to the topic hello, and you will see it in this screen, okay? So this is me subscribing to a topic hello, the abstract chat room. So if you send something there, your name or anything, you will see it in here. Yeah, that's all.
Y ponte que la ya, wifi, no saben mucho.
No estás compartiendo pantalla. ¿Qué pasó? ¿Has caído? No estás compartiendo pantalla. No sé, es que no sé qué pasó. ¿Qué? Nos gustaría estar. Tenés aquí. ¿Nos están oyendo? Sí, están oyendo. Okay, so on the top, you can check if the messages are being received by the server, and on the bottom you have Wi-Fi credentials, and the address. Okay? You see it or not? If you have an ESP32, you have to change this line.
Pues, ahí tú sí con esto.
No, vamos. Pueden ser master, ¿no? Pero no receivers.
No sé. Es que,
Bueno.
o sea, ahora estoy intentando, porque lo que no estoy claro son los pines de... ¿Vale? O sea, hay sitios que dicen que en realidad no tienen pines de hardware.
Hacerlo por TWI.
O sea, define aquí el wire begin, te pones dos números y puedes estar escribiendo ese detalle.
Gracias por hardware, por software.
Pero, claro, ponerle una adresa a este.
Bueno, ya está. Se hace un chip con esto, o sea, lo miramos tranquilamente, ya lo documentamos bien. Lo suyo sería que empezáramos a usar esto de knowledge o la documentación de la KM para documentar todo esto, porque todos los años nos pasa algo así. Yo estas cosas yo nunca me acuerdo, ¿no?
Start looking at the electronic Pásate ya.
Bueno, pero la idea es que lo empiecen a entender. Que funciona, ¿no? Sí y no. Sí te da, pero no, claro, lo que tiene es el no te pedí todo. No se puede poner uno más grande para tenerlo más sencillo. Bueno, no sé si se puede, pero en el fondo cuanto más se ve, cuanto más se le pone. Si le pones otro, seguramente lo hará así, pero claro, pero más sencillo. Por eso, cuanto más sensible, más pasa y yo me digo que no, vale.